So this is a talk about how to do lots of things, sometimes whilst juggling. Coroutines. This is what we're going to be looking at. Let's start with the very basics. What actually is a coroutine? I know that even if you're the sort of person who's been using coroutines on a regular basis, well, there's a lot of rote learning in the way that we learn programming sometimes, and I sort of want to deprogram that. I think it's important that people understand the principles behind things more than understand like the building blocks of how to put them together in a piece of code. And what I want to do is start again from the beginning and talk about why coroutines exist in the first place. What is the point of them? And obviously how we use them. So firstly, how we use them in Kotlin, like the base language stuff, and then putting them into context within Android. Then we're going to have a hands-on writing a pin number app. Then we're going to look at scopes and things that reduce the lifetime of a coroutine, which makes them safe to use. Then there's going to be a second hands-on where we're going to write a warning light app. And then we're going to talk about how coroutines are run, you know, what the actual coroutine library does at a low level. So we're going to talk about dispatchers, where do they run? And we're going to talk about the context finally. So that's what we've got. Buckle in. Let's get going. Let's start with what is a coroutine. To talk about that, we need to talk about how we used to do things, how we used to manage multiple tasks at once. So a coroutine is about managing lots of things, or is that process. The old-fashioned way of doing that was using threads. So I don't know if anybody here remembers Java before Kotlin, or even Kotlin before coroutines. But the way that we used to manage that was if you had 4 things to do in parallel, they needed to be done at the same time, then we would run 4 threads to do those things. And a thread is a heavyweight thing. A thread is difficult to manage. It slows things down because there's huge overheads that are associated with threads. Generally speaking, there is a limit to the number of threads that devices can run. So basically, the overhead in terms of memory for a thread is about 1 megabyte. So that tends to be the limit that you hit. You know, if you run 1,000 threads, you're going to hit a memory limit pretty soon, especially if you're trying to run that on a phone. So there was a problem. We were trying to run lots of things all together, and each time we wanted to start a new task, we would start a new thread, we would get the overhead of that. But it was recognized that if you pick one of those tasks, so let's say we pick task 1, let's say it's a thread that reads something from a disk and sends it via the internet. We actually find that most of the time that thread does nothing at all. It's completely idle. So if we look at what a thread that reads something from the disk and sends it via the network might do, well, the first thing it's going to do is request a read from the disk. And obviously hard disk, whatever technology it is, much slower than a CPU. So CPU is going to sit and wait for that request to finish. Then it's going to do a little bit of computation, work out the packets that it's got to send on the network, and then it's going to send it via the network. And then it's going to have a big, long wait for the network to come back to us. And then it's going to process that data. So frankly, in this diagram here, the amount of time that is set aside for actually doing something versus waiting is hugely exaggerated. In fact, this thread is waiting like 99% of the time. So there was a question of, well, can we use those gaps whilst a thread is idle to do something useful? Can we sort of compress the amount of threads that we're using just by using those idle periods? So if we look at those 4 tasks again and break it down into when a thread is actually doing something versus when it's idle, it might look something like that. And you might notice that if you just rearrange those a little bit, you could produce something that looks like that. That's all the same amount of stuff. All those same jobs are being done. They're being done slightly slower because look, the end point here is slightly more time than by the time they finished here. But the overhead of the threads would mean that probably there's very little in it. We need to play around a little bit with the timing of things. So notice with these blue ones, for example, to fit them all in, these blue ones start a little bit later. But as long as we're okay with that, we can basically fit all of that work that was previously on 4 threads into 2 threads. So this is the difference between what we used to call, well, what we call parallel working and concurrent working. So the name for that is concurrent. The difference between parallelism and concurrency is about doing lots of things, and parallel is about doing things well, in parallel, you know, all at the same time. Concurrency is not necessarily about doing things at the same time. So coroutines are about concurrency, threads are about parallelism, which gives us what our definition of a coroutine is. A coroutine, very simply, is a task that can suspend. It can suspend as opposed to block. We'll see what that means later. So let's take an example of, this is not a concurrent task. This is not a coroutine. This is a normal Kotlin function. We are placing, this is to toast some bread. We are placing bread in a toaster. We're waiting 2 minutes for the toaster to do something. And then when the toaster's done something after those 2 minutes, we're taking the toast out. So a thread would look like this. We would place the bread in the toaster. We would sleep whilst it's toasting, and we would take the toast out. If we look at that as a coroutine, we write this as a suspending function. We have switched from a thread.sleep, which blocks the thread, to a delay, which doesn't block it. It tells the coroutine library, hey, I'm available, you can use me for some other purpose. And notice as well that that is what suspend means. That's why we have a suspend function. A suspend function is one that can suspend, that can tell the coroutine library that there is space here, there's space in time for you to be able to do something else whilst I'm waiting for something to happen. So that's what suspend means in the context of coroutines. So how do we run a coroutine to start with? Well, in Kotlin, one way to fire and forget, I mean, there's a few ways, but one way that's a fire and forget is just a launch. We have a coroutine scope.launch. That coroutine scope, by the way, dictates the lifetime of the coroutine. We're going to go into a lot more detail about what that really means. But basically, you fire and forget, you say coroutine scope.launch, and now you're inside a coroutine. Now you can use suspending functions. So that leads us to our first hands-on. We're going to run a coroutine to show a pin number briefly. So let me show you how that will look. So if you've got the repository again, it's linked at the bottom of the slides there. So download that repository, and what you should find is there's a simple button that just says show pin, and I'll show you how that's going to look whilst we let me share this. So what we're going to do is simply this. We've got a button that says show pin. If I press the show pin, it's going to show me my pin for 5 seconds, and then it's going to disappear. So that is task 1, is to produce the function that does exactly that. And if I go back to the slide here, you should have everything that you need to do that. So I will give people a couple of minutes to get going on that one. Shout if you need any help. But after a couple of minutes, I'll step in and we'll see how to do that. So yeah, there's the slide. So to run a coroutine, use coroutine scope.launch. To get a suitable coroutine scope, use remember coroutine scope. And to pause the coroutine, use the delay function. Those are the 3 pieces that you need in order to succeed this hands-on. Go ahead, Zane.
Hello, can you hear me?
Yeah, I can hear.
Yes, so I want to know what do you mean by suitable coroutine scope? Use remember coroutine scope. Can you
So
please explain?
in this, yeah, in this particular case, a suitable coroutine scope would be just calling remember coroutine scope. So that is a coroutine scope that lasts as long as the composable is in the composition. So sort of basically a little bit like how long it's on the screen for.
Okay.
So has anybody managed to get that on the screen for 5 seconds and off yet? Nice one, Chris. Yes. Excellent. Raise hand, go ahead. I can't hear anything, I'm afraid, if you're speaking.
Yeah, so like if we click the button 2-3 times, multiple coroutines will start, right? So how do we handle multiple clicks?
That is a very good point. In this particular case, I wouldn't worry about it. We're going to go into how we can manage that sort of thing a little bit later, and about scopes and contexts and lifetimes and also effects that get cancelled and start again. So for now, don't worry about the fact that if you press it 30 million times, it's literally going to happen 30 million times.
Yeah, cool.
Yes, sorry, the project is with Android Studio Koala. So would anyone like to share what they've done? That's potentially a step too far for a few people. But if anyone's willing to, otherwise I will,
Yeah,
I will go ahead. Yeah, go ahead, go ahead. Share your screen.
yeah, so screen is good. Yep. Is my screen visible? Sorry.
Your screen's visible, but not Android. Yeah, it is now, Android Studio.
Yeah, so I have started a coroutine here and non-click. So like for now, I'm just disabling the button. So once you click, a coroutine will start and it will launch a relay. And then after the thing is complete, I'm just enabling it back.
Perfect, absolutely perfect. Anybody else have any other any comments or any different ways of doing that?
Yeah, one more option is like we can use launch effects. So that also I tried and it worked. So if you want, we can use like this also.
Yeah, launch effect would be one of the answers to how can I stop this from happening
Yeah, so
n
there we
times if I click it n times.
yeah, we don't need the context here. So the launch effect has the context.
Yeah, but no, that's perfect. That's a grand solution. That's almost byte for byte what I had here. So grand. All right. You can stop sharing now. We will move on to the next thing. So did everybody see that, by the way? So what we had was coroutine scope.launch and a delay, and then show pin equals false. It was as simple as that. Okie dokie. Okay, so next important thing about coroutines, particularly in Kotlin, we've been talking generally about coroutines up until now. Obviously, we've had that hands-on, but specifically about Kotlin now, coroutines are cancelable in Kotlin, and that is so enormously important. Coroutines are cancelable. In fact, let me just unshare that. Here we go. Yeah, Kotlin coroutines are cancelable. So the way that we cancel them is, well, we can simply cancel them. We say when we launch a coroutine, we get a handle to the coroutine in the form of a job object, and the job object is the thing that can be cancelled. So if we take this example and put it into, hang on, Kotlin around. I'll share this window just for now. Share this one instead. So if we take this exact example and run it here, what we are going to find is that here we've got the launch coroutine, and then so the launch coroutine is to print something, delay, and then print something else. But we are going to launch it, then after half a second, we're going to cancel it. So if I press run, what we'll find is that that first print line gets printed, but the second one doesn't. Now, that's because we've cancelled the coroutine, but the reason behind this is again, the nitty-gritty that's so important, that's lacking from just learning this by learning blocks of code. You can only cancel the coroutine once it has yielded to the coroutine dispatcher. So one way of yielding to the coroutine dispatcher is using a delay. So a delay goes back to the coroutine dispatcher and it tells it to do whatever it needs. You know, here's 120 seconds of time, do what you need with it. So that is yielding to the coroutine dispatcher. Another way of doing it is literally calling the yield command, the yield function, which is like saying delay, but without giving a delay. So it's saying to the coroutine dispatcher, let's just see if things have been cancelled. Let's see if you need to do something more important. But if not, I'll take the, I'll come back, please. Or you can, there are various ways of managing this yourself. So you don't necessarily, you know, if you don't want to specifically call yield or delay, you can check whether, you can manually check whether you've been cancelled. So good question there, should we put yield for safety? Not necessarily, not necessarily. Generally, generally within coroutines, you have a tiny little bit of work and then a long amount of delay and then tiny bit of work, because that's just how background tasks end up decomposing. Tiny bit of work, long delay, tiny bit of work. So generally, you don't need to bother about yielding. You don't need to bother about manually finding whether the you've been cancelled and you need to do something else. But if you're doing something, you know, there are some tasks that are entirely CPU intensive. So an example I gave in a blog is if you are writing a program to count to 100 billion, that takes an appreciable amount of time. And there's nothing in there that is delay based. You know, you're just literally incrementing a variable 100 billion times. And it takes on my system a couple of minutes to do that. There is no point at which that could ever be cancelled, because there's no point at which you yield. So you've got to kind of keep in your mind whether the code that you're writing needs those yield or those determining whether the coroutine has been cancelled or not. You know, manual determination. But generally speaking, for most I/O tasks, which is what most coroutines, you know, most background work is within Android, it's either UI or I/O tasks. Most of that you will never need to worry about that fact. Okay, so let's move back to here. So that's cancelling a coroutine. Now, we are getting to the point of, you know, this is the real exciting bit. We are getting to the point of understanding where coroutine scopes come in. So a coroutine scope is like a container for a coroutine that limits its lifetime. Important to understand understand that one completely. A coroutine scope exists to limit a coroutine's lifespan. So you put a coroutine inside a coroutine scope. We saw that that launch earlier. You have to do coroutine scope dot launch. You can do a launch inside an existing coroutine, but basically you're still using the coroutine scope of the parent coroutine then. But basically every coroutine is launched inside a scope. Once the scope ends, all the coroutines inside it get cancelled. So here's an example again of our placing bread in a toaster and waiting and then taking the toast out. Actually, if the scope of the coroutine dies during that time, then you're not going to finish your coroutine because the coroutine inside it gets cancelled. Now, placing that within an Android case of understanding these scopes within Android, well, there's a number of commonly used coroutine scopes. You've obviously can create your own, and there's other ones other than the ones on this list, but the commonly used ones are remember coroutine scope, which is what we used before. Now, the lifetime of the coroutine scope that you get by calling that function equals the lifetime of the composable in the composition. So when the composition dumps your composable in which you've called remember coroutine scope, then all the coroutines that you've placed in that scope are going to get cancelled. Launched effect, we mentioned that one a little bit earlier. It's not a scope itself, launched effect, but it launches a coroutine into a scope which lasts until that variable that you pass it, that x, lasts until that changes. So basically it's tied to what's usually the parameters of the composable, and when one of those parameters changes, when the state of the composition changes, then the launched effect gets cancelled and restarted, and that coroutine lasts again for as long as the new value of that x variable remains in place. If you go to the Android views world, a sort of parallel to that is obviously you have lifecycle owners within views. Not many people know about views these days. It was a complaint that I heard about from the Google team, that actually views are still quite important, but new developers only learn Jetpack Compose. Anyway, the Android views are bound. The views are dictated, have a life cycle, and we have a coroutine scope that is bound to that life cycle if we use lifecycle scope. And those are the UI ones. Remember coroutine scope, launched effect, lifecycle scope. Those are the ones we usually use for UI. Again, there's a little bit of play, and maybe there's good reasons why you wouldn't use them for UI, but generally that's what they're used for. For I/O, we usually kick off I/O tasks within a view model. So we have view model scope within Android view models. And yeah, that exists for as long as the view model exists. Obviously, a view model sits outside of the user interface and has its own life cycle. And the scope that's associated with that is view model scope. We also have global scope, which is a bit of a special one in that it never dies. It's a coroutine scope that is designed to last as long as the application is alive. So it's a bit of a dangerous one to use, because anything that you launch into global scope is never going to disappear. It's going to be there forever and ever and ever. Which means that you need to manage the life cycle of any coroutine that you launch, that you launch in that manner. That doesn't necessarily mean never use global scope. It just means that usually there's better scopes to use. And if you do need to use global scopes, syncing, for example, is potentially something that you would use global scope for, or analytics stuff that needs to run in the background for the entire time that the app is alive. That might use global scope. If you do need to use that, you just need to manage the life cycle yourself. So that's some examples, which takes us to the next hands-on. So the second task is to make the warning sign flash. I think that our pin number app, which just shows a pin number for 5 seconds, doesn't warn the user enough that this pin number really shouldn't be shared with anybody else. So we're going to make a red flashing warning sign that tells us not to share that pin number with anybody else. So if you have a look at the warning light composable, for me it's on line 69 of main activity, but may differ for you because you've obviously added code in. But that warning light composable has a flash state, and what you want to do is, for as long as that composable is on the screen, you want to toggle that flash state every, let's say, 500 milliseconds or whatever you fancy. So yes, that is the next hands-on. Again, I'll give you a couple of minutes for that, but put hands up if you need any help. I will. I'll come along. Other people are obviously very willing to answer as well, which is wonderful to see our growing community here. Yeah. So remember, coroutine scope and launched effect are two that give you a scope that lasts as long as the composable is in the composition. So you want to use one of those. Give us a wave emoji or a thumbs up or something when you're done. And most people are. Nice one, Dean. Okay. Okay, lots of thumbs up. Okay, wonderful, wonderful. Anyone want to share their solution to that? Okay, I'll jump in and share mine then. Okay, so my solution was to use launched effect, but with unit, which obviously never changes. And then we can simply have a while true and toggle the flash state, delay 500. Simple as that. Did anybody get something different? Did anybody do something different?
Tom, we can use key as a flash state.
I'm sorry, I missed that.
We can use launch effect with key flash state.
Okay.
I've shared the code in chat.
Got it. Okay. And feel free to share code if you fancy. But yeah, that's yeah. Good point.
Yeah, I did the same. I just used the key flash state, and I got rid of the while loop.
Okay. Okay. Yeah, that makes sense. That makes sense. So using this, let me just pin this like this. So what we should have is, regardless of how you've done it, and yeah, it is a good point, you can use the key of flash state. You should have a flashing warning like that. And looking at my code here, obviously, if you've done it the slightly different way, it's not necessarily true. I want to just talk about how completely weird and alien this code is. It's really, really strange coming from a place of Java and threads and having to manage threads so carefully. It's really weird, is it not, to be able to write a piece of code that just says while true, do something. So that's the first thing that's really weird. While true, and there's no conditions to that while loop. There's no break anywhere. There's just a delay. There's just the fact that the coroutine can be cancelled that is managing that. So while true, in this particular case, completely fine. And that goes against all our instincts from previous worlds, where, you know, writing while true is usually a very dangerous thing to do. But here it's completely fine. So that's the number one thing that's completely weird. The second thing that's completely weird is we have just fired this coroutine out and forgotten about it. We have no handle to that coroutine. We've just asked it to launch, and we've gone with it. How weird is that to a world of threads where you just have to minutely manage every single thread that you've ever created? And if you ever created a thread that you forgot about somewhere in your code, and it just, you know, just carried on, and each time that bit of code was hit, it created another thread, and you're not just screwing up your app, you're screwing up the whole system. So anyway, I think it's worth just pausing to see what kind of code we can now write as a benefit of coroutines that would have just been completely alien previously. So would everybody like to hazard a guess as to which thread, if we look at the thread that this is running on, which thread is handling all of this?
Main thread?
Yeah, exactly that. So if we say log.v thread.currentThread.name and run it and have a look at the logcat, and we'll press the show pin button. There's it. There's our thing there. It is indeed running on the main thread. Now that, in this particular case, is fine, because actually it's not doing anything other than toggling a variable. But it's not. It's, you know, even though we've got coroutines which are very, very efficient about using the space within threads, it's still not a good idea to tie up the main thread. The main thread is there to do UI stuff, and that's pretty much it. And if we're using the main thread for anything other than UI stuff, even if it's a tiny little bit of time, then we're still taking a performance hit on our UI. So if we're doing stuff that is non-UI, we need to tell the coroutine dispatcher that we want to run it somewhere else. So back to the presentation then. So if we're doing something that's not UI, we need to direct our coroutine to an actual dispatcher. So there are 3 well-known dispatchers within Android. Actually, you can create your own, and sometimes there are other dispatchers available, but really there's 3. There's dispatchers.main, which is the main thread. It's completely bound to that single main thread. There's dispatchers.io, which tells the coroutine dispatcher that this is likely to be a long-running IO task. So that is a dispatcher that is particularly efficient for that purpose. So networking or disk reads or that sort of thing. And the other sort of task that you might want to do is short that are fairly intensive. So, for example, sorting a list or parsing JSON or something like that. And for that, we have dispatchers.default. So those are the 3 dispatchers. And again, you can create your own if you've got, you know, back in the old Java days, you had thread pulls and executors, and you were able to, and these days with coroutines, you're able to convert an executor into a dispatcher if you want to manage this sort of stuff yourself. Go, Ahmed, you raise a hand.
Yeah, thanks, Tom. So do you recommend using doing parsing in default or IO thread?
Good question. So generally, default I use for if I'm doing that as part of a UI. So for example, if within my UI I need to sort a list for the purposes of display or parse some stuff that we've obtained from, well, the user or some source, but as part of the UI, then I switch from the main into default. Generally, with if I've just got it through IO, if I've just got it through the networking, then I don't bother switching to default from IO. I will do parsing on the IO thread. That may not be correct. I'm interested to know if people do that differently, but that's the way I handle it. It seems to be pretty safe.
Yes, I do the same.
Yeah. Yeah, unconfined dispatchers.unconfined. We don't really touch this for underneath. As for the layer underneath where Android really runs.
So Tom, one question here. So if I have an API call, okay, then I might want to use a dispatcher.io, and then I have a let's say the API returns a long list of data, and I want to process it. So we could switch from IO to default one. But is this the better approach, or we could do this in the dispatcher.io itself?
I do that in IO. I do that in IO itself.
Yeah, so we don't need to switch to default. Cool. Yeah, just
No.
wanted to know that.
No, you don't need to. I think if you actually look at the configuration of the thread pool that's behind IO and the thread pool that's behind dispatchers.default, there's not a lot of difference between them. And actually switching that context doesn't, I can't see a benefit of getting it. It's not strictly, that's why I said I'm interested to hear other people's opinions here, because it's not strictly what the documentation says you should do. It says default is for those intensive calculations like parsing, and IO is for networking and dis reads. But I think you're good. I think you're good.
Cool. Yeah, got it.
Okay, so how about how to set the dispatcher? Well, we use with context. Using with context, we can take a coroutine that's running in one particular dispatcher and switch it to a different one. Simple as that. So the block that goes inside that with context is the IO task that's now running on dispatchers.io. It's a good convention if you're writing a library or something like that, and you know that you are writing a function that is going to go off and do some IO work. It's a good convention to switch your context within your function. Don't require the calling code to switch context for you, in other words. So the context switching should be done within the function that requires it, not requiring the calling code to do so. So the with context goes inside your function there. But actually, if you're just launching a new coroutine, then you can specify the dispatchers.io directly inside your launch. that argument actually ends up doing exactly the same thing as that argument there. They end up being a context. So that word context, the with context there, what does context actually mean? Yes, Ivan makes a good point. You should write main safe code, in other words. So everything really should be able to be run on the main thread, on the main dispatcher. So that word context. This is how I like to see a context. This is how I like to understand a context. A context is a little bit like metadata that's attached to a coroutine. And I picture that as sort of luggage tags attached to it. So one of the pieces of metadata will be its dispatcher. One item within the context is the coroutines dispatcher. The coroutine can have a name that's useful for debugging. No more than that. It's just a name that's used within the system. A coroutine can have a parent job as well. So you can attach a coroutine to a different parent job than the one that it was actually started by. And all of these things form part of the coroutine context. Now, context items, you can add your own, it's basically, if you look at the way that is defined deep within the coroutines library, coroutine context is actually just a map that you can add your own items to as well. But coroutine context is the metadata for the coroutine, and the dispatcher uses that metadata to determine how to run your coroutine. So in the same way that we can use with context dispatchers.io, we can set those other context items as well. We can build our own context. So we can say with context dispatchers.io, and then we can use the plus operator to add different parts of the context on. So we can specify dispatchers.io plus a given coroutine name plus the parent job that it's part of. If you don't mention a particular context item, then it just takes the context. It just takes the item from the parent that's run it. Now, drum roll, we're getting towards the end of this session because we're going to see how this all comes full circle. And this is kind of the exciting bit for me, because this is where these terms that we've learned, this context, this scope, the idea of a job, the idea of coroutines and delays and dispatchers and things like that, this is where it actually all shrinks and gets a little bit simpler, I think. So a job, we saw a job earlier. We saw code that looks like that. We can launch a coroutine and we get a job object. A job is just a handle to a coroutine. Simple as that. But it can also contain other jobs. So if we launch a coroutine from that job, sorry, if we launch a coroutine from another coroutine, then it sits, unless we've specified otherwise, it sits inside the same job. It has the parent job of the coroutine that launched it. But we can also launch coroutines directly into another job. We saw that with the with context, where we can specify a parent job for the coroutine. So I can launch a completely fresh coroutine from somewhere totally else within my code, and I can launch that directly into the job, into some other job that I have a handle for. Now, if a job's cancelled, his children are cancelled too. Is this ringing some bells? Because previously, let's look at the slide that we had previously. A coroutine scope defines its lifetime. It's the slide that we had before. And once a coroutine's scope is cancelled, then all of the coroutines inside it are cancelled as well. So what's the difference between a scope and a job? They're both containers for coroutines, and they both are designed to, or have the effect of limiting the lifetime of the coroutine that's inside it. Well, actually, the answer is there's no difference at all because they are the same thing. Now, this is how, inside the coroutines library, this is how a coroutine scope is defined. A coroutine scope is just a handle to a coroutine context. Seems a bit weird, right? So a coroutine scope is just a wrapper around this coroutine context. And a coroutine context has a job. So why, so a coroutine scope is just a wrapper for a coroutine context, which holds a job. So why, what's the point, right? Why have we got this different name for a context that holds a job, which we call a scope, versus just a context? And the great Roman Elizarov, the father in inverted commas of Kotlin, described that as well. He used the analogy of ships and ropes on a ship. So I don't know if any of you are sailors, but there's different ropes that have different purposes with, on a ship. There's sheets and halyards, and I don't even know if I'm pronouncing that word correctly, but you know, there's all sorts of different ropes, but they're all ropes. They all do the same thing. Or they're all built the same way. But if you use them, they're used for different purposes. And he used that analogy to say that scope is just a context that is designed around a job. So a job limits the lifespan of a coroutine, and a coroutine scope is just a context that has a job. I hope that is clear. So those terms are all interconnected, all interlinked, but it comes down to there is a context. The context has a job, and if the context has a particular job, then we can call that a scope, and that's a shortcut to saying this lifetime limiting thing. Okay, so we're getting towards the end now. I only have a summary left, so I'll go through the summary and then I'll ask if there's any questions, and then that's pretty much it for today. So in summary, a coroutine is a task that can suspend. That's the definition of a coroutine. And in Kotlin, that's represented as a suspend a suspend function. That's what suspend means. A coroutine gets launched into a coroutine scope, and that coroutine scope is a bounds for the lifetime of the coroutine. The coroutine also has context, which is basically just metadata describing how it should be run. And a running coroutine is represented by a job object. That job object can contain children, and when the job is cancelled, its children are as well. And the parent job of a coroutine is part of its context. So we get to a coroutine scope is just a context with a job. So that's it from me. Any questions? Go ahead, Ahmed.
So we can say that scope is like the root of a tree of branches of jobs.
No, it depends what you mean by root in that particular case.
I mean, like if a job can, as you said, can have children, and children can have children. So if we have branches and sub branches of jobs, and then so the scope will be a single point, and as an entry point.
I see. Yes. Okay. So what you end up having if you've got coroutines in coroutines is you have jobs inside jobs inside jobs inside jobs, and really actually any one of those jobs could be a scope. You would just need to construct a coroutine context using that job as part of the context.
Mm-hmm.
So there's nothing particularly special about the root one. That's you know, we would normally call that a scope, absolutely, but any one of those in the middle could be a scope as well, because a scope is just the job. It's just a context with a job.
Okay, so can you tell me the reason for implementing it as an interface? I'm thinking about the design concept about using an interface that holds an parameter, you know. So is there a reason for this?
Implementing what exactly as an interface?
The coroutine scope, you showed that it is an interface, right?
I see. Yeah. So back. Boom, boom. Yeah, implementing it as an interface. I'm not totally certain on that one. I don't know if anybody else has an answer for that. Certainly, there are a load of extension functions on coroutine scope, which you know, the fact that it is aside from a coroutine context, you know, it's a launch, for example, is an extension function on coroutine scope, and async, which is another way of launching coroutines, is an extension function on coroutine scope. In terms of why it's an interface, I presume so that we can create objects that that implement that, and the async and the launch as well.
Yeah, thanks a lot, Tom.
Any further questions? Go ahead, Zach.
Yes, can you please describe the supervisor scope?
Yes, supervisor scope. Okay, so this this one is this is a scope where it's about child failure. The failure of a child doesn't cause a supervisor scope to fail, and it doesn't affect its other children. So what you need to understand with supervisor scope is how that is different from coroutine scope, which is a function we haven't hit here. So coroutine scope with a lowercase c is a function that's used for parallel decomposition of tasks, and that means that let's say that we had the example of a coroutine that was used to toast a piece of toast, but let's say we're making beans on toast, right? Let's say there's two tasks with making beans on toast. That's one, you need to make the toast, and two, you need to microwave some beans. And you would use coroutine scope and launch two coroutines within that coroutine scope. Again, lowercase c. It's so annoying that that word is reused. It's a rubbish name for that function, but lowercase c coroutine scope is the name of it. So that's what we got to say. But you would launch those two coroutines, one for making the toast, one for making the beans, inside the coroutine, inside coroutine scope. Yeah. And if any one of those children failed, like the microwave doesn't turn on or something, then that would mean the whole, it throws an exception. That would mean that the entire coroutine scope dies. So your whole job, not just the microwavey bit, but also the toasty bit, both of those get cancelled and die. A supervisor scope is only valid. You can only understand what a supervisor scope is in comparison to coroutine scope, because a supervisor scope is one in which if a child dies, the parent doesn't die. It doesn't take the parent down with it. So that's what a supervisor scope is. There's value in that. I don't want to go into too much detail, but yeah, that's what a supervisor scope is.
Okay, thank you.
Go ahead, Ahmed.
Can you later, or if you have a reference, show an example about loading list, infinite list for scrolling, optimized with MVI and for snapshot state list to avoid any unnecessary recomposition?
Okay, that's, I would say, somewhat out of the topic of this talk, but yeah, MVI is an interesting one in itself.
Yes,
maybe we'll do a session on that.
I was thinking about, because this workshop is about concurrency, so I'm thinking about async loading and make it to a real life example about infinite scrolling. So maybe if you have free time for this.
Yeah, okay, understood. That's yeah, a few things we can do there. Might be an interesting blog.
I have my approach. Maybe I can show you later if you are free.
Sure. Okay. Sure.
Okay.
Find me on LinkedIn. That's the best place to find me. But yeah, I'm very interested to have that conversation. There's a few things there that are potentially interesting.
Yes. Thank you a lot.
So structured concurrency is a term that's been mentioned in the chat there, and that's the concept of structured concurrency is this concept really of jobs inside jobs inside jobs inside jobs. But that is the structure of structured concurrency, as I understand it. Does anyone else want to add more to that in terms of what structured concurrency is? No, okay. Yeah, the structure that we're talking about there is down to what owns what, and sort of most importantly within coroutines, what gets cancelled when parents die. It's that parent-child relationship. Okay. Any further questions? No. Okay. Yeah, go ahead.
The exception handler. Is this the best way one can handle the exception, or is there a best practice for this?
It is worth saying that well, if you're handling exceptions, there's a couple of approaches within Kotlin. I don't think anything is particularly worse or better than any other from a point of view of coroutines, except to say that the way that code like this, where are we? Yeah, the way that code like this handles cancellation is via a cancellation exception. So if we cancel here, then this line is going to throw a cancellation exception. So you have to manage that cancellation exception. If you've got an old-fashioned exception handler, try catch, you have to manage that cancellation exception carefully to make sure that your code really does cancel at that point. Because if you just did a blanket try catch, then there is a danger that you wouldn't cancel when you needed to. You would see that cancellation exception and not handle it properly. So that's the only thing that I would mention there. I don't think there is a particular better way of doing things.
I have one last question, please.
Go ahead.
I don't think it might be off topic, but I want to make in a view model, and you do navigation to another class, so the view model of class A is still there. And if you do loading for infinite screen again using async, the coroutines will still firing, and the APIs is get and receive. So when navigation happens, and if you do it in a traditional way like view model scope dot launch and so and you navigate it to another screen, the APIs is still calling, and you should cancel the APIs. So I made it. I exposed the suspend functions in view model to composable. So you know, when and I did it in launched effect. So once the screen navigated to another screen, the scopes will be cancelled, and when returned back, the launched effect will fire again and re-execute. So what do you think about this approach? I know it might be complex to say it all in one.
I think I've got to see your code.
Yeah.
I think is the answer.
In short,
It's a little bit hard to keep all that in my head all at once. To be
okay, it's not in short. Does exposing suspend functions from view model to composables, is it good?
I still can't picture that.
Yeah.
I'm afraid.
Yes.
That's hard to say without seeing your code.
Okay.
If anybody else has an opinion on that, please shout. But you're reaching the end of my ability to picture things without thought. Hey.
Yeah, so like if the view model is scoped to the screen composable, it will automatically get cancelled when you move from. If you're
Yes.
using compose navigation, it will automatically get cancelled, right? So we don't have to expose a suspend function to cancel this.
Yes. So I'm thinking about if this good approach or bad, or if there another something that.
Yeah,
But
so we don't have to expose the suspend function. Like if you tie the coroutine to the view model scope, the view model will get destroyed when you navigate to a different screen. Automatically, this will happen. So you don't have to manually handle this.
That is my understanding as well.
No, view model will not destroy if you navigate it. It will destroy only if you pop the composable. But
Like you're navigating to a different screen and still the view model is in the scope.
yes, because when you navigate from list to detail screen, you will not pop the list. This is what I'm thinking of. But yeah.
Okay, in that case, there are lifecycle events, so you can consume that, and based on that, you can take a call. Like in the launched effect, you can have a on pause event, which you can pass to the view model that can cancel this job.
Yeah. Yeah. Thanks a lot. Thanks, Tom. I'm sorry for taking some time from your session.
No, not at all. Not at all. Good to talk.
Yeah.
And again, share code if you can. So we'll wrap up there though. Just to remind you, those are the next events, but also any shares, anything like that on social media. If you've enjoyed the session, very gratefully received. We're trying to build a community here so that more people that get to know about these sessions, the better. But those are the next two. And share, like, yeah, that's it. So thank you very much, everyone, for joining. Appreciate it very much, and hope to see you in a couple of weeks for the next one. Take care. Bye bye.
Bye bye.